slide.
Hey y'all, welcome back. So today we're working on a dot product homework. So let's go through and we'll compute a bunch of dot products and see what else we've got going on here. Looks like we're finding the angle between two vectors and probably doing some other stuff too. So the way that we compute the dot product, if you recall from the lecture, is let's say we've got two vectors. So one is, we'll just call them sort of generic A, B, and then we'll say the other one is like, I don't know, P, Q. And if we want to compute the dot product, what we need to do is multiply the corresponding components and then add those two values together. So like here we would multiply the x components or the horizontal components, A times P. And then we would also multiply the vertical components, B and Q, and then we'd add those two products. Okay? So what we get is a scalar out of this. If we have a three-dimensional vector, it works pretty much the same way. We just have to also, we'll have like a third product that we'll add here. So like when we get to B, we'll multiply these two as well. So for the first one, we have 6 times 2 plus 3 times -4. And this is something we can put in the calculator. You can probably evaluate this without a calculator. So this is U dot V. And so yeah, let's go ahead and type that in. Pull up the calculator real quick. There we go. Okay, so we've got 6 times 2 is 12, plus 3 times -4 is -12. Oh, okay, so this is going to be 0. And there's a consequence, or not a consequence, but there's something notable about when you have a dot product that is 0. Anytime you have a dot product that's 0, that indicates that you've got perpendicular vectors, and we have a special word for that when we're talking about specifically vectors. When the angle between the vectors is 90 degrees, we call them orthogonal. Okay, so I might make a little note here. It doesn't really ask about that, but it's worth noting as we go through these. Anytime we hit a dot product of 0, I just want to make a quick shout out to the fact that they're orthogonal, because eventually I'll be asking questions about orthogonal vectors. So U and V are orthogonal. Okay, that is true when the dot product is 0. So just making a little note about that. You don't have to include that in your answer. That's really just for me, so as we go through these, we get to some questions about okay, so look, number 2, find the values of T that make the vectors orthogonal. That's kind of where we're going with that. So I'll do C, so I don't have to move the calculator, and then we'll do B and D. So the way we're going to calculate this is pretty much the same. So I'm just going to copy and paste the work here. So U dot V is going to be, in this case, 5 times 3. And if you don't actually see a coefficient on here, but you do have the standard unit vector written, we're going to assume that the coefficient is 1. So it'd be like 5 times 1, plus 3 times, 5 times 3 plus 1 times -1. So we're multiplying the horizontal components and the vertical components, and we are going to add those two products together. So we've got 5 times 3. Probably don't need a calculator for this one either, but just to be safe. So it's going to be 15 plus 1 times -1 is -1, so it should be 14, I think. Yeah, 14. So these are not orthogonal, no big deal, but there's nothing really special about how these are oriented. So B is a three-dimensional vector. Oops, there we go. So B is a three-dimensional vector, and so the way we're going to compute a dot product of three-dimensional vectors is very similar. The only difference is we're going to have 3 things that we're adding together. So here we've got 10 times 2. There we go. So 10 times 2 plus, looks like negative 3 times 6 plus 6 times 9. So notice here, we're multiplying our first components, our second components, our third components, and then we'll just add everything together. So we've got 10 times 2 plus negative 3 times 6 plus 6 times 9, and we get 56. For D, we do basically the same thing. Okay, so calculating this dot product, there's not going to be really much of a difference between how we solve all these. But so for the first one, we've got negative 4 times 8. Looks like we've got 6 times 6, and then we've got 9 times 0. So again, one that we could probably do mentally, but just to be on the safe side, I'm going to type it in. So we've got negative 4 times 8 plus 6 times 6, that'll be 36. And then the last one, 9 times 0, which will be 0. I don't really need to type that in because adding 0 is not going to do anything, but I'm going to go ahead and just do it anyway. Okay, so we get 4. Okay, so there's the first 4 problems, or at least A, B, C, D for number 1. That's how you compute the dot product. A little note here that the only thing I really want to point out, and this is going to be relevant for the next problem, is that when the dot product is 0, you know the two vectors are orthogonal, meaning that they're essentially perpendicular. So for number 2, it's asking, find the values of t that make the vectors orthogonal. So we're going to set it up, just like this, but we're going to create an equation that's going to have a t as one of these numbers, and then we'll just set the whole thing equal to 0. So in order for the dot product to be 0 here, we need to say that 2 times 3 plus negative t times 2 is equal to 0. And so we're going to solve for t here. So I'm just going to clean up this equation. 2 times 3 is 6, minus 2t equals 0. From there, we will subtract 6 from both sides and divide both sides by negative 2, so we get t equals 3. So t is 3. When t is 3, that means that these would be orthogonal. And we could see that visually. If you were to actually plot this out, 2, negative 1, 3, 2, you'll see that they actually do, those two vectors are separated by 90 degrees. So for B, the only thing to really point out here versus the other ones is that, notice there's no j component on the second vector, so we're just going to assume that it's 0. So negative 3t times, just kind of put that in parentheses here, so negative 3t times negative 6 plus 2 times 0. Okay, notice how the j component's missing here, so it's kind of like just saying like plus 0j, okay, equals 0. So let's clean that up. Negative 3 times negative 6 is going to be 18, and then we still have the t, plus 0 is just nothing, equals 0. So dividing both sides by 18 here is going to result in t being 0. So if t is 0, then those two vectors will be orthogonal. For C, okay, we've got a cosine. And it looks like D's got some cosine stuff in there too. All right, very good. So same deal here. We're going to set it up very similarly. Cosine of t times negative 6 plus negative 1 times 3 should be 0. And this is just kind of the rough equation here. Let's clean it up so it looks a little more approachable. We've got negative 6 times cosine t plus, let's see, negative 1 times 3 would be negative 3, so minus 3 equals 0. And we need to solve this, so we've got cosine of t, or negative 6 cosine of t equals 3 after adding 3 to both sides. If we divide both sides by negative 6, we get cosine of t equals negative 1/2. So from here, you'd use the unit circle to solve this, since negative 1/2 is one of those numbers on the unit circle. So I'm going to pull that up and say, okay, well, where are the x values negative 1/2? And I can see pretty clearly they're going to be at 2 pi over 3 and 4 pi over 3. We do want to write all the solutions, so we are going to, so here's how you would write that. T equals 2 pi over 3 and 4 pi over 3. And if I was just asking for solutions between 0 and 2 pi, that would be it. But this doesn't say anything about restricting the solutions. So what I really need to do here is say that we can add any integer multiple of 2 pi and get more solutions. So there's actually infinitely many solutions, but this is just an efficient way of writing that. All right, if you want a little bit more detail on how to solve these trig equations, go back to, I guess it was unit 2, no, maybe unit 3, where we learned about solving trigonometric equations. No, that's about as good as I can get it to fit on there. Okay, it looks like D is going to turn out kind of similarly. Let's get rid of that unit circle for now. There we go. All right, so we're going to set up a similar equation. We've got cosine t times sine t plus sine t times negative cosine t. Throw a little negative sign in there. And that should equal 0. Going a little off the page here. Let's just make this a little smaller since it's taking up kind of a lot of room here. Okay, so I'm gonna just clean this up a little bit. We've got cosine of t times sine of t, and then multiplying a positive and negative makes that minus, so minus cosine t sine t. When does that equal 0? Well, that is always going to be 0, because anytime you subtract something from itself, you get 0. So it doesn't really matter what t is here. So we could say t could be anything. So t, we'll say it could be all real numbers. All right, this is a statement that will always be true, and we call that an identity. Okay, any statement that's always true, any equation that's always true, regardless of what the variable is an identity. And in that case, we say that the variable could be anything. All right, let's take a look at E. E and F looks like it's just an extension here, so we're going to set up similar equations. So for E, we've got 1 times 2t plus 4 times negative 5 equals 0. So after we simplify a little bit, we get 2t minus 20 equals 0. And then, so adding 20, we get 2t equals 20. And then dividing both sides by 2, we get t equals 10. For F, we'll set it up similarly. Okay, so we got something kind of weird going on with F. We've got the horizontal component is 2 plus e to the t. Hopefully that doesn't cause too many problems here. It's probably been a while since you've solved any equations with the variable as an exponent. I mean, we haven't done it in this class yet, So the last time you would have done this was last year in Algebra 2. So I'll do a quick little review here, but I don't think this one's going to end up being too complicated. Anyway, that times 1 plus -1 times 2. And in order for these to be orthogonal, once again, it's got, the dot product must equal 0. So, so let's simplify this. If we're multiplying by 1, that doesn't really change anything. So we've got 2 plus e to the t. And then -1 times 2 is going to be -2. So -2 equals 0. 2 minus 2 is 0. So like this and this, we'll just cancel it each other out. E to the t equals 0. So luckily, kind of lucked out here because you don't really need to know how to solve an exponential equation here as long as you understand that this could never be 0, okay? E to any power is going to be a positive number. It can never be 0. So we're going to say there's no solution here, okay? So maybe I'll make a little note out to the side that says raising a number to any power will never be 0. Even if you raise it to the 0th power, surprisingly enough, because remember when you raise it to a 0th power, it equals 1. So there's just no solution here. All right, so that's number 2. Let's take a look at number 3. So for number 3, it's asking for the angle in between the vectors. Now, some of these will be more obvious than others, and so I do encourage you to kind of sketch it out first. But there is a formula that will give it to us if we can't figure it out by the sketch. And I'm just going to do a really rough sketch here on some of these just to see if we can sort of find the answer without using the formula. So here we've got like 4 is going to be, over 4 up 4 is going to be at like this 45-degree mark. And 2, 0 is going to be right here. So this one should be really obvious. You shouldn't need to use a formula for this one, although you could check it. Yeah, this one's just going to be 45 degrees. So sometimes it's really obvious. It won't always be so obvious, and so I'm not going to, rely on the sketch for all of them. So I'll just kind of use the sketch until I find one that it is not as obvious, and for that I'll use the formula. So for B, just to get an idea of what this is going to look like, we've got 2 times the horizontal unit vector, so that's just going to be a horizontal vector with a magnitude of 2. Okay, so we'll just say looks something like this. And then this is -3j. Okay, so -3j would be down here. So we can see that the angle between these two vectors is 90 degrees. Yeah. Don't really need a formula for that one either, although, again, if you are just feeling kind of lazy and you just want to use the formula, you'll get the same answer. So these are orthogonal. If we find the dot product of these, we get 0. For C, I think we're going to have to use the formula on this one, but let's just kind of take a quick look and see what's going on here. We've got one vector that is 4, 1. Okay, so somewhere over here. And then -2, 3. So this one is not as obvious. It looks like it's going to be obtuse, just from my rough sketch here. But so we're going to have to use the formula. So let's actually go through and see what the formula is. So to find the angle between two vectors, this angle theta, this is a formula that was given to you in the notes. So if you want a little bit more discussion on like where this is coming from, go check out the lecture video. But it will be the inverse cosine of this big fraction where we have the dot product divided by the product of the magnitudes. So the magnitude of u times the magnitude of v. Oops. Let's see if I can, there we go. Formatting here is a little funky, but that'll work. Okay, so really we're just going to be like plugging in the values that we have here. So we've got the inverse cosine of u dot v. So that's going to be the dot product, which we discussed up here, how to calculate that. So we have 4 times negative 2, which is negative 8, and 1 times 3, which is 3. So negative 8 plus 3, okay, which is negative 5. And then we've got, let's see here. The magnitude of u is going to be the square root of a squared plus b squared. So 4 squared plus negative 2 squared would be the same as like 2 squared. And so that would be, let's see here, 16 and 4 would be root 20. Oops. Oh, no, that's right, root 20. For the magnitude of vector v, we have the square root of negative 2, wait a minute. I think I messed up here. That should be 4 squared plus 1 squared. My bad, y'all. So that would be 16 and 1, which is square root of 17. Sorry about that. And then over here, we've got the square root of 2 squared plus 3 squared. It would be negative 2 squared, but negative 2 squared is the same as 2 squared. So we have 4 plus 9 is 13, okay? So this is something that you're just going to type in the calculator and get an answer. So I've got the inverse. Well, let's make sure I'm in degrees here. It's going to default to radians, so if you ever reset your memory, go back and change it. And so we've got the inverse cosine of negative, let's do a fraction. And we've got negative 5 divided by the square root of 17 times the square root of 13 and so we get about 109 degrees. Or I guess if we're rounding, 110 degrees. And that kind of matches up with our sketch here. You know, we were kind of expecting it to be obtuse slightly, and this is slightly obtuse. So that kind of matches up here. Okay, so again, we're just doing the sketches as like a way to say, hey, can we figure this out? You know, like A and B, you can see really clearly what the angle between the vectors are, but it's not always going to be like that. So feel free to use this formula each time. All right, so for D, I'm just going to jump straight to the formula here. I'm not sure why it's not letting me copy this. There we go. Oh, wait, I've got the calculator up. Okay, so for D, same deal. In fact, we're going to use this formula for D, E, and F. E and F are three-dimensional vectors, so you know, you could try to sketch it, but it's not gonna, it's very difficult too. And not really worth the effort unless you're a skilled sketch artist. Okay, so let's calculate the dot product for D. That would be 6 times 8 plus negative 2 times negative 5. Okay, 6 times 8 is 48. Negative 2 times negative 5 is 10. So we get 48 plus 10. So that would be 58 on top. That's the dot product. And then the magnitude of vector u is going to be the square root of 6 squared plus 2 squared, or negative 2 squared, but that's the same as 2 squared. So let's see here. We get 36 plus 4 would be the square root of 40. And then the magnitude of v would be 8 squared plus 5 squared. So 8 squared is 64, and 5 squared is 25. (64) plus 25 is going to be, let's see, that'd be 89. And so now we're ready to put everything in the calculator. So I'm just going to copy and paste this so I don't have to retype everything. And so we've got, let's see here, 58 over the square root of 40 times the square root of 89. Those are the two magnitudes we're multiplying in there. Okay, and we get about 14 degrees. Okay, for E, same thing. It's just going to take a little bit more work to calculate these because we've got 3 dimensions, but no big deal. We've got 2 times 7 plus 5 times -1 plus 3 times 4. So 2 times 7 is going to be 14. 5 times -1 is going to be -5. 3 times 4 is going to be 12. So let's see here. 14 minus 5 is 9. Plus 12 is 21. So to find the magnitude of these vectors, you're just going to use sort of like an extended Pythagorean theorem here. It really is based on the Pythagorean theorem. If you're curious, let me know, and I'll go through the proof of why this works. But basically, we'll have 2 squared plus 5 squared plus 3 squared, and we'll take the square root of the whole thing. So 2 squared is, oops, get rid of this calculator here. My bad. So 2 squared is 4. 5 squared is 25. 3 squared is 9. Okay, 4 and 25 is 29, plus 9 would be 38. So that would be the magnitude of vector u. The magnitude of vector v we will find similarly. Okay, so this will be the square root of 7 squared plus 1 squared plus 4 squared. So 7 squared is 49, 1 squared is 1, 4 squared is 16. 49 plus 1 is going to be 50, plus 16 will be 66. Yeah. All right, so now we're ready to go. We're ready to type this in the calculator so we can get our answer. So let's see how many degrees we get. Now let's pull back that calculator. So we've got the, let's put it right there, the inverse cosine. Just copy this again. And we get 21 divided by the square root of 38 times the square root of 66. So we get about 65 degrees. All right, letter F. We're going to do the dot product. Same way we did it before. I'm going to move it down here because this is probably going to take up some space. So we got -3 times 6 plus 5 times -3 plus 2 times 1. Again, I'm just multiplying these corresponding components. We get -18. 5 times -3 would be -15. And 2 times 1 is 2. So -18 minus 15 is going to be -33, plus 2 is going to be -31. The magnitude of vector u is going to be the square root of -3 squared, or just really 3 squared, will make it easier to type, plus 5 squared, plus 2 squared. So let's see here. 3 squared is 9, 5 squared is 25, 2 squared is 4, 9 and 25 is 34 plus 4 should be 38. So the magnitude of vector u is root 38. Is that the same? Okay, yeah, all the numbers are the same here as in E, but just sort of rearranged. Okay, I don't think we'll be as lucky with V. So V is going to be the square root of 6 squared plus 3 squared plus 1 squared. So 6 squared is 36, 3 squared is 9, 1 squared is 1. 36 plus 9 is going to be 45, and then plus 1 would be 46. Okay, now we're ready to start typing away. So we get the square, or the, not square, the inverse cosine of negative 31 over the square root of, it's still 38, and then the last one's going to be 46 here. All right, so about 138 degrees. So you can see, you know, you might need to use the formula. You want to try, like, if they're easy to sketch and you have kind of a gut feeling like, hey, I might be able to figure this out without the formula, it's definitely faster to do it like that, like we found in A and B. But at the end of the day, you can just use the formula. So yeah, this was about, what was it, 138, I think? Yeah, about 138 degrees. Okay, so that's it for number 3. Let's take a look at number 4. And it looks like with number 4, we are trying to find the measure in degrees formed by the vectors. Okay, so same kind of deal here. We're trying to find this angle measure, but like in between the two vectors. But what's interesting is they don't actually tell us what the vectors are here. They just tell us the dot product and the magnitudes. So it's actually going to be easier than what we did above because we won't actually have to calculate the magnitudes, or the magnitudes are down here, or the dot product. It's given to us. So finding this angle measure is going to be a heck of a lot easier in number 4 than it was in number 3. All right, so let's go ahead and copy this formula. Although I will change the u and v to a and b, because that's what these vectors are named. And so notice that all this information is given. Even though we don't have the vectors themselves, we don't really need them. We could probably figure them out, you know, what they are, but it's not asking for that. It's just asking to find the angle between them. So we just need to plug in the important information. Oops. What is going on here? There we go. So the dot product is 100. The magnitude of A is 30. The magnitude of B is 20. And so we just go to calculator town here. The inverse cosine, well here, let's just do what we were doing earlier, of 100 over, oh, we don't even need the square root here. So it's just 30 times 20. And we get about 80 degrees. All right. B is going to be worked identically, except we're going to plug in different numbers here. So the dot product for B is, oh, let's get rid of this calculator. I don't want that to happen again. Is negative 24. And the magnitude of A is 8, the magnitude of B is 9. And so that's pretty much it. We're going to go ahead and calculate it in the calculator here. So inverse cosine of, I'm not even going to bother copy and pasting because there's no decimals or anything like that. Should be pretty easy to type. Negative 24 over 8 times 9. Oops. And so we get about 1 degree. Is that right? Did I type that in right? Oh, I did cosine. I should have done inverse cosine. My bad, y'all. That's what happens when you don't copy and paste. It's like 1 degree, that doesn't sound right. Okay, there we go. That sounds a little bit better. Okay, so about 109 degrees. All right, so that wraps up number 4. We've got one last problem here with a couple of different parts, but we're going to look at number 5. All right, so for number 5, it's asking for us to add vectors a and b. Now, they don't actually tell us what a and b are. If they did, that would make it kind of easy. That's what we did in the last lesson, where we added vectors. We just add the horizontal components, add the vertical components, and we'll have our answer. But here we have to actually find the vectors first. And so just as a little reminder on how you find the vectors given the magnitude and the direction angle is the x component, or the horizontal component, component is going to be the magnitude times the cosine of the angle measure, or the direction angle. Okay. Actually, I wonder if I can throw in a little dot here instead of a little. Is that going to be here? Let's see if this will work. Yeah, that looks a little better. Okay, so that's how you find the horizontal component. And then to find the vertical component, you are going to do the same thing, except use sine instead of cosine. Okay, so I just want to kind of remind you of how to find both of those components on the vector. So what we'll do here, the strategy is going to be to actually find vector A and vector B first. We don't need to simplify or anything. We're just going to leave it as is and then just type in everything in the calculator at the end, because we're going to end up adding these two vectors. So vector A here will be the magnitude 5 times the cosine of pi over 3. Actually, this one we probably don't even need a calculator because, we'll go ahead and probably use a calculator anyway. Anyway, cosine of pi over 3. And then we've got 5 times the sine of pi over 3. Okay. So there's vector A, the first one. And then vector B, let's make this a little bit smaller so it's not so crammed in here. Yeah, that's a little better. Is going to be, it has the same magnitude, so 5 times the cosine of pi over 2, and then the sine of pi over 2. Yeah, you know what? I'm kind of going back on what I said. I think maybe we just use the unit circle here. I don't think we really need a calculator for A. We'll use a calculator for B. The calculator is not really going to be necessary for this one. So if I want to add these together, I have to figure out what these equal, right? So there we go. So A plus B is going to be something comma something, right? And the somethings are going to be the sums of the corresponding components. So I'm going to add this plus this as my first component, and then I'm going to add this plus this as my second component. So we've got whatever this equals plus this, and we'll evaluate these. And then for my horizontal or my vertical component, I've got this thing plus this thing. So basically, we're just adding the corresponding components. So let's simplify this a little bit. Let's pull up the unit circle. Let's start by looking at pi over 3. At pi over 3, the cosine is going to be 1/2. And then the sine of pi over 3 is root 3 over 2. The cosine of pi over 2 is going to be 0, so that makes this kind of simple to simplify. And then the sine of pi over 2 is going to be 1. We're going to have to make this a little smaller to, or can we just move it over? Let's see. Yeah, I'm just going to make it a little smaller, just to make it so I'm not trying to squeeze it in too much. Okay, so let's go ahead and just simplify this now. So 5 times 1/2 is 5/2. 5 times 0 is 0, so adding 0 is just nothing. And then over here, we got 5 times 1 is just 5. And then 5 times root 3 over 2 is going to be 5 root 3 over 2. You could simplify this one, like if we found a common denominator, and I'll just show this as a separate step, 5 would be the same thing as like 10 over 2, and then we can combine these and say it's 5 root 3 plus 10, over 2. So that would be as simplified as you could get that one. You definitely could put this in the calculator to get a decimal. We'll do that on the next one just so you can see how that will play out. But this would be the exact value of this vector. Okay. So let's do B, and we're going to set it up and kind of solve it the same way. Okay, so we're going to find vectors A and B. In this case, vector A would be 13 times the cosine of 25 degrees. With the cosine of 25 degrees, 25 is not going to be on our unit circle, so actually let's just go ahead and get rid of that since we're not going to need it anyway. And then our vertical component will be 13 times the sine of 25 degrees. Our B vector has a magnitude of 40, so it'll be 40 times the cosine of 100 degrees and 40 times the sine of 100 degrees. So A plus B is going to be like this plus this as our horizontal component, and then we'll also add our vertical components to get the vertical one. So we've got 13 cosine 25 plus 40 cosine 100, and then I might just, can I just hit enter? Yeah, this is going to be too much to fit on there. So that'll be the first component, and then the second component, which I'll just continue kind of down here, is going to be 13 sine 25 plus 40 sine 100. And so this is just, we're just going to put this in the calculator, okay? So let's bring out the calculator one last time here. I'm in degrees. Let's make sure I'm still in degrees. Looking good. And so we've got 13 cosine 25 plus 40 times the cosine of 100. And I get about 4.8. I guess we'll go 3 decimal places here. So we'll say A plus B is 4.836, comma, or not equals, but should be approximately equal to. really that you can't simplify this anymore if you're giving an exact answer. So here it kind of makes more sense to just estimate. And then for our vertical component, we've got really the exact same statement here, except we'll have sine instead of cosine. Okay, so we get about 44.886. All right, so let's take a look at some physics problems here. On number 7 here, we're trying to find the work done by trying to drag this table across the floor. So we're pulling with a force of 45 pounds at this 30-degree angle measure, and we're dragging it 20 feet. But ultimately what you need to do is just multiply or find the dot product of the displacement vector and the force vector. Okay, so the displacement vector here is going to be this 20, 0, because we're dragging it 20 feet to the right. Okay, so 20, 0. And then the force vector is going to be this vector right here. So to find the horizontal and the vertical components of this, this is something that we did in the previous lesson where we multiply the magnitude here, which is 45, by cosine and by sine of the direction angle. So the horizontal component would be 45 times the cosine of 30, and the vertical component would be 45 times the sine of 30. So I don't want to say that in the lecture video what I said was incorrect, but this is going to be, I think, a way easier way of kind of getting to the answer here, is just find the dot product of these. So in other words, like the amount of work done is equal to the displacement vector times, let's get that dot, since we're doing a dot product, times the force vector. So the work done here is going to be the dot product of 20, 0 and 45 cosine 30 times, comma, 45 sine 30. And since we know how to find the dot product, this should be pretty easy to calculate. So here we can kind of avoid, the whole, finding the projection and all that. This is going to be a much more direct way of getting there. But let's go ahead and start calculating this out. So this will equal. First thing I want to do is simplify these expressions. Okay, so using my unit circle, I can identify that the cosine of 30 degrees is root 3 over 2. And then sine of 30 degrees is going to be 1/2. So I'm just going to kind of leave this here alone, since we're going to be putting it all in the calculator at the end anyway. So let's see here. We've got 20 times the 45 cosine 30, and that's in degrees. Throw that little degree symbol in there. Oops. There we go. Plus 0 times, and notice, with the 0 times, it doesn't really matter what I'm going to multiply by because it's just going to turn out to be 0 anyway. So, but I'll throw it in there just to let this be complete. And then, so let's go ahead and throw this in the calculator. We've got 20 times 45 times square root of 3 over 2. We could give an exact answer here since it is one of those common angles, but I'm going to just get a rounded answer here. There we go. So we've got 20 times 45 times the cosine of 30 degrees. And so we get approximately 100 and 38 point, we'll say 826. Now, as far as the units are concerned here, you know, this is going to be pound feet. It's kind of a weird unit here. Pound feet. I don't know. Yeah, kind of a weird thing here, but that's what it is, okay? Or, wait, hold on. I'm sorry, not feet, pound feet. It should be feet, foot pounds. Jeez. I don't know if that makes it any better or worse, but that's just what they're called. Yeah, kind of a weird unit there, but 138 foot-pounds. So that represents the amount of work that would be done if you drag this table across the floor with a force of 45 pounds at 30 degrees. All right, well, that's the last question here. Hopefully you feel a little bit better about this material. As always, let me know if you guys have any questions. And other than that, y'all have a great day, and I'll see you next time.